Now let us think about our design of battens. Okay, now so battens, first we have to decide the center to center spacing, that is the spacing between the compression member. Then after we have to go for the spacing between the battens. Okay, now then we have to go for the length of the battens, then depth of the end pattern and depth of the intermediate pattern, then after thickness of the batten. Okay, now after designing this, whether it is satisfying the shear force or bending moment, that we have to check it. Okay, let us move on to the design of battens. Okay, first we should do the spacing between the member D. Okay, and this spacing from here to here, this is nothing but spacing. Yes, so this is nothing but D plus 2 times of CYY. Okay, let us go for the design one by one. So first one is design of spacing between the two channels. Spacing between two channels. Okay, so here the formula is 2, that is the moment of inertia of the section with respect to individual axis we are going to equate. Okay, so Iyy plus area into d by 2 plus cyy the whole square is equal to 2 times of Ixx. So this gap is nothing but d by 2 plus cyy. Okay, with respect to individual section and their moment of inertia we are equating now. So we all know that here gets cancelled. Iyy is nothing but 310.8 into 10 to the power 4 mm power 4 plus area individual section. So 4564 into d by 2 we have to calculate plus cyy. So 23.6 mm the whole square is equal to Ixx. So Ixx value is nothing but 6362.6 into 10 to the power 4 mm power 4. Okay, now how we should get I by D value? So 4564 into D by 2 plus 23.6 the whole square is equal to 6322.6 into 10 to the power 4 minus this Iy value comes into this side, then it becomes minus into 10 to the power 4. That value is nothing but 60.518. 60.518 into 10 to the power 6 mm power 4. Okay, now d by 2 plus cyy the whole square is equal to 60.518 into 10 to the power 6 divided by 4564. Then d by 2 plus 23.6 is equal to root under this value 60.518 into 10 to the power 6 divided by 4564. Then it becomes 115.51 mm. Here d by 2 is equal to this 115.51 minus 23.6. Therefore, d is equal to 2 into that value. It becomes around 183 mm. Say the spacing between those two member is equal to 200 mm. So first step is over. Have you got this? So the first step, this d is equal to 200 mm we got. Okay, next we should move on to the spacing between the two batten. Okay, this value c, this we have to calculate spacing between the two batten. So 2.2 spacing between the two battens, that is C. So what is the formula? So we already discussed while discussing the for procedure, okay? R over YY of single section, C divided by RYY of single section should be less than 50. This is one condition. Second condition is C divided by RYY of single section should be less than 0.7 times of Ke. Okay. So here C value is, we have to calculate RYY of the single section. We noted that RYY is the value of 26.1 mm. Okay, should be less than 50 mm. Then C becomes, okay, C should be less than 1305 mm. This is with respect to first condition. With respect to second condition, C divided by 26.1 should be less than 0.7 times of Ke value is 83.83. We know that, okay? So then it becomes 0.7 into 0.7 into 83.83 into 26.1. It becomes 1531.57. So therefore C is equal to 1531.57 mm. So among these two conditions, we have to choose the less value. Okay. So lesser than those two values we have to choose. Therefore, C provided is equal to 1300 mm. Okay, so here it is 1500 plus, here it is 1505. So in between these two, the lesser value we have to choose. Okay, now so 1300 is less than these two values, so that's why we have selected this. Okay, now we should mark that value. C is equal to 1300. C is equal to 1300 mm. Okay, so second part is over. Next, third one. That is nothing but distance between the centroids. Distance between the centroids. Centroids of the two channel. Okay, this is nothing but S. So from here to here. Okay. So D plus 2 times of CYY is the value. So S is equal to D plus 2 times of CYY. So D value we have selected that 200 plus 2 into CYY is 23.6 mm, correct? So if I am going to substitute this value, S becomes 200 plus 2 into 23.6 mm. It becomes 247.2 mm. Okay, so in the figure we have to mark. So S is equal to 247.2 mm. Okay. So next 2.4. In that first one, end batten design. So end batten size. Size in the sense we are going to have only depth D. Okay. So first one, effective depth. Effective depth. That is D dash. So D dash should be greater than or equal to S. Okay. This is the condition. So S value we know that 247.2 mm. So D dash we can provide 250 mm. Therefore, overall depth D. Okay, so here we have to note it down. So D dash, they are saying that from here to here, they are saying that D dash. Okay, so D in the sense overall depth. So here one edge distance E and here another edge distance E we have to add. If I am going to add these two edge distance, then automatically I can get overall depth. So the formula is overall depth D is equal to D dash plus 2 times of edge distance. So edge distance formula is 1.5 times of D, D naught. So D naught is nothing but bolt hole dia. Okay. So dia of bolt we have to choose. Dia of bolt we have to choose that 20 mm, assuming it is 20 mm. Therefore, dia of bolt hole becomes 20 plus 22 mm, then becomes 22 mm. Therefore, edge distance E equal to 33 mm, say 35 mm. Therefore, D is equal to how much? So 250 plus 2 into 35. So 320 mm is our overall depth of end batten. So that we are going to mark it in the figure. So overall depth of end batten D is equal to 320 mm. Okay. Similar way we have to calculate for intermediate batten. Okay. So this is 2.4.2, correct? Intermediate batten. Intermediate batten design. The same way, first one is effective depth. Effective depth. So which is nothing but D1 dash. So D1 dash should be greater than 3 by 4th of D dash. This is class number 7.7.2.3, page number 51. It is available in IS 800. Okay. So if I am going to have 3 by 4 into D dash is 250. So it becomes 187.5. 187.5 mm. So I can say 190 mm. It should be greater than, okay now. So 190 mm is my requirement or provided. Next, I have to go for overall depth. That is D1. The same way, intermediate batten. Okay now. So this I am going to consider, the column is going to be continued here, then this will be the intermediate batten. So this is my D1 value. So this is nothing but D dash D1 dash. Okay. So plus 2 times of edge distance will give the answer of overall depth. So overall depth D1 is equal to D1 dash plus 2 times of E. So 190 plus 2 into 35 mm. So 190 plus 2 into 35 mm. So 260 mm is the overall depth of intermediate batten. So that I am going to mention in the diagram. D1 is equal to 260 mm. Okay. So all these things are over. Next, I have to design the thickness of the batten. Thickness of the batten. So thickness of the batten. T. So with respect to the class 7.7.2.3 from page number 51 of IS 800. Okay. T should be greater than or equal to 1 by 50 times of D plus 2G gauge distance. So assume gauge distance, normally we are going to take it as 2.5 times of D. Okay, so 2.5 into diapole we have assumed that 20, so it becomes 50 mm. Okay, therefore T is equal to 1 by 50 into D value we have selected that 200 mm. Okay, 200 mm. Okay, so 200 plus 2 into 50, so that 300. So 200 plus 2 into 50 is 100. Answer divided by 50. It becomes 6 mm. Okay. Therefore, T is equal to 6 mm. So minimum we have to provide the thickness T is equal to 6 mm. That I will mention in the diagram. So T is equal to 6 mm thickness of the batten. So almost everything over except the length of the member. So length of the batten is from outer to outer edge, so that this D plus this breadth of flange on either side. By adding this, I can get the total length L. Okay, so length of the batten is equal to L. So L is equal to D plus 2 times of breadth of flange. So breadth of flange is 90 mm. So 2 into 90 becomes, here it is 200, 360 mm. Sorry, 380 mm is the length of batten. So length of batten L is equal to 380 mm from this end to this end. Now the only thing, that is the size of the battens have been arrived such that 380 mm length, depth, if it is end batten, then the depth is uh, 320 mm and the thickness is 6 mm. If it is intermediate batten, then the depth is 260 mm and the thickness is 6 mm and the length is 380 mm. So this is how our design of batten. Next, we should move on to the design force on battens. Okay, 2.5. Design force on battens. Design force on battens. So we know that from class 7.7.2.1 page number 51, Vt is equal to, that is transverse shear. Transverse shear Vt is equal to 2.5 percentage of axial force P. So 2.5 divided by 100 into axial force is 1100 into 10 cube. So the answer becomes 27.5 kilonewton Vt value. Okay. Next we have to go for Vb, that is longitudinal shear. longitudinal shear VB is equal to the formula they have mentioned Vt into C divided by N into S. Whereas Vt we have know that into 10 cube Newton. C they have we know that C value is 1300 mm, S value is 247.2 mm. So C value is 1300 mm and S value is 247.2 mm. Then N value. So N is nothing but the number of parallel plane. Number of parallel plane. Okay. So here here one plane is there and here another plane is there, so that n is equal to number of parallel plane, that is becomes 2. Okay, so n equal to 2, therefore vb is equal to vt 27.5 for 3 into c 1300 divided by 2 into 247.2, it becomes 73.31 kilonewton. 72.31 kilonewton is the value of VB. Okay. Next, shear stress. Sorry, moment. So moment M. So the formula M is equal to Vt into C divided by 2 into N. If I am going to substitute Vt is equal to 27.5 into 10 to the power 3 into C value is 1300 into 2 into N value is also 2. Then the moment becomes 8.9 into 10 to the power 6 Newton mm. Now check for transferring shear. Okay, shear stress is equal to VB by area of batten. Area of batten should be less than Fy divided by root 3 into gamma m naught. So we all know that Fy is equal to 250 Newton per mm squared and gamma m naught value is equal to 1.25. Okay. So VB value we calculated that 72.31 kilonewton. So 72.31 into 10 to the power 3 divided by area of batten. Which area is least? So we can have end batten and intermediate batten. Okay, for thickness both are same as 6 mm, but the breadth is going to be changed, that is overall depth. So overall depth of end batten is 320 mm, but intermediate batten is 260 mm. So which one is least? 320 mm and 260 mm. So among them, the intermediate batten size is less. So we have to choose that. If the intermediate batten is safe to transfer, then automatically the end batten also will transfer the load safely. So 260 into 6. So it becomes 72.31 over 3 divided by 260 into 6. 46.35 should be less than Fy value is 250 divided by root 3 into gamma m naught. It becomes 115.47 Newton per mm square. So the condition is satisfied. Condition is satisfied. Hence, safe to transfer the shear stress or shear force. Next, we should move on to the moment. that is bending stress. So bending stress. Okay. So bending stress here, the formula, bending stress, the formula is equal to 6m divided by t square, 6m. Okay, that is m by z simply. Okay, that's why they have given. So the formula is 6 into m value is 89, sorry, 8.9 into 10 to the power 6 divided by thickness is 6 mm and d value is, which one is less? 260 mm is less. Okay, so 6 into 8.9 exponential power 6 divided by 6 into 260 square, then it becomes 131.656 Newton per mm square. So this value should be less than Fy by 1.1. Fy by 1.1 becomes 250 divided by 1.1 is equal to 227.27 Newton per mm square. So the condition is satisfied. Condition is satisfied. Hence, safe to transfer the moment also.